metallic bonding for Cambridge iGCSE Chemistry. So Cambridge requires the theory of metallic bonding and metallic structure, an explanation for electrical conductivity, and of malleability and ductility. So the model for the structure of a metal is one of a giant lattice of metal atoms. That is, large numbers of atoms arranged in a regular way. So we have layers of atoms layered on top of each other, and this goes on forever. It's a giant structure. Millions upon millions of atoms arranged in layers in this way. And we call the whole structure a giant metallic lattice. So to explain metallic bonding, we need to develop this model of metallic structure a little. Rather than having atoms, which we see here, nucleus and outer shell electron, we use the idea that metal atoms lose their outer shell electron, which of course are negative, to leave behind a positive metal cation, a positive metal ion. So we now have a giant lattice of positive metal ions surrounded by electrons that are no longer located in the outer shell of a particular atom, but are able to move freely throughout the structure. So we have, to repeat, a giant lattice of positive metal ions surrounded by a delocalized sea of negative electrons. So delocalized is the term that is used to describe the situation where electrons are able to move freely throughout a particular structure. So we now have the metallic structure as a giant lattice of positive metal ions surrounded by a delocalized sea of electrons. These positive metal ions form strong electrostatic attractions for the sea of delocalized electrons. So if we take a central metal cation, it's attracted to the sea of delocalized electrons in all directions, and therefore it's held in place. So these strong attractions, electrostatic attractions between the positive metal ions and the sea of delocalized electrons make up metallic bonding. And of course, those attractions are strong, and there's a great many of them. So that to break those attractions and to separate the metal particles, the metal ions, would require a great deal of energy. And hence, most metals have high melting and boiling points. Electrical conductivity. Metals conduct electricity as solids. We can explain this by looking at the structure we have just described, that is, a giant lattice of positive ions surrounded by a delocalized sea of electrons. The delocalized electrons, which are the charge carriers, are able to move throughout the structure. So this electron here can move wherever it wants to go. And that is true for any electron. That movement, because of the fluid nature of the sea of electrons, can occur without disrupting the metallic bonding. That is, there's no energy barrier to that. So these delocalized electrons are able to move throughout the structure, carrying electrical charge. Hence, solid metals are electrical conductors. Malleability and ductility. Malleability means the ability to be bent or hammered into sheets. Ductility is the ability of metals to be stretched into wires. Both can be explained because of the fluid nature of metallic bonding. That is, we have a cationic lattice, a lattice of positive metal ions surrounded by a sea of delocalized electrons which are able to move throughout the structure. If a force is applied to a metal, then those layers are able to slide over each other. There's no particular energy barrier to that because of this fluid nature of the metallic bonding. The exam wording in mark schemes for this explanation is: the layers of ions slide past each other easily. Well done for finishing. You may want to find some practice questions, try your textbook, and then past paper questions. For more related chemistry classes, look at the playlist or the links in the description of this video. If you found this class helpful, please recommend it to a friend. Please like, subscribe for new classes and last-minute exam tips.